In the last video, we saw how for an open set U in X, we can describe the morphisms from U into an affine variety Y. And now we want to see that if actually both the domain and the target are affine varieties, so you look at morphisms from X to Y themselves, then there is a very nice description of all morphisms of this form in terms of the coordinate rings of X and Y. And so here's the claim, kind of corollary, is that when you are given affine varieties X, Y, there is a bijection of the morphisms from X to Y and the K-algebra homomorphisms from KY to KX. So here the map goes in the opposite direction. And the reason why this arrow is turned around is because the correspondence is given by sending the morphism F to the K-algebra homomorphism F star, so the pullback by F. Okay, let's see how this proof works. So by definition, F star, of course, goes from the regular functions on Y to the regular functions on the pre-image of Y. But we have seen the regular functions on all of Y are just given by the polynomial functions, A of Y. And the pre-image of the entire target is, of course, the entire domain X. And then similarly, we have here A of X. So it is true, at least, that this map here is well defined. F star is really a K-algebra homomorphism from I guess it should be A of Y to A of X. Sorry. And conversely, now we need to go in the opposite direction. So we prove this bijection by giving an inverse map. And so let's give ourselves here a K-algebra homomorphism as above. And assume that, well, Y is an affine variety, so it sits inside some AN. And then we do the same thing that we had before. We let Y1 to Yn be the coordinate functions here. And the idea is if we know that G is equal to F star, then we can actually use that to reconstruct what F should have been. Because as we saw, pulling back the coordinate functions exactly gives us, well, the coordinates describing F. And so indeed, what we can just do is we can plug in the coordinate functions into this string homomorphism G, and we get some elements of A of X. And then we just set F to be the map from X a priori it goes to AN, given by these regular functions. What we need to show now is that, first of all, this is a morphism and it lands in Y. And then we have a chance to prove that, that this is the inverse to this map. To do this, we do one crucial calculation, which will kind of solve all the rest of the arguments. And that is, well, we compute what F star does on any H. So in other words, on any polynomial on the target here, like what happens if we pull it back by F? Well, by definition, we just have, we calculate H of F of X, and F is given by these components. And they, by definition, were given by G of Y1 up to G of Yn. And now the crucial thing is this is a K-algebra homomorphism by definition, right? It sits inside this set here. And so we have these, we apply this K-algebra homomorphism to a bunch of functions, and then we apply a polynomial. And because algebra morphisms commute with addition and multiplication, we can kind of switch the order. Instead of first computing G on these things and then plugging into a polynomial, we can first plug the Yi into a polynomial and then evaluate G on this thing. And then the evaluation at the point X comes at the end. So somehow that was a crucial step here. Here we used that this is a K-algebra homomorphism, and this allows us to draw this G out. That's a crucial equation. And then this tells us all the things we want. So first of all, we need to show that f, the image of x under this map, actually is contained in y, so that we can have a chance to get a morphism from x to y. And then indeed, what we just show is that, well, whenever you have any function which vanishes on y, then by this equation, f star of that function is equal to g of that function. But then, while g is defined on the functions on y, and h vanishes on all of y, so h is actually the zero function in here. And then K-algebra morphism sends the zero function to a zero function, so this is zero. So in other words, for this function h vanishing on y, if we pull it back by f, we get the zero function on x, which means for all x in x, f of x lands in the vanishing locus of h. This is true for all h in here, and this implies that f of big X, the image of f, is actually contained in the vanishing locus of all functions inside I of y. And then by the Nullstellensatz, if you take vanishing locus of ideal of a variety, then you just get the affine variety back. And so indeed, f of x is a subset of y. That was nice. And then the second thing is that f is a morphism, because indeed all of its coordinates are given by regular functions on x, plus the proposition above then tells us this is a sufficient criterion to be a morphism. And then the final thing, now we have gotten ourselves this morphism, and then we want to check that it is actually that somehow this is the direction going from G here, going to here, constructing this f, and then going back. This gives the identity, so this gives G back. So we have to show that f star is equal to G. But indeed, this is kind of, again, this equation here, because you see here f star of h is equal to G of h. That's what we checked. And so this proves one of the bijections, and the other is, I guess, also not so hard to see. And so this finishes the proof, and shows us that we have this this equality between morphisms from x to y and the K-algebra morphisms of the coordinate rings in opposite direction. We can now refine this a bit and then say, if we restrict to isomorphisms from x to y, then this corresponds to isomorphisms on the other side. And indeed, I mean, if f is an isomorphism, then it has, by definition, some inverse G. And then going to the f stars, the claim is that then f star is an isomorphism, and the inverse is given by G star. And for this, you just have to check that, well, the G star is the right and left inverse to f star. But then if you do such a composition, that's basically in all of mathematics. That's the rule. If you have two pullbacks and you compose them, then it's the pullback under the composition where you have to make sure that you get the order right. But then G composed with F is the identity on X, and pulling back by the identity is the identity. So G is a right inverse to G star is a right inverse to F star, and then the same kind of calculation shows that it's also left inverse. And so indeed, isomorphism corresponds to isomorphism. To have a concrete example here, we can look at a slightly complicated affine variety given by its vanishing locus of y minus x squared and z minus x to the 3 inside A3. This turns out to be a curve like this, and this is called the rational normal curve in this case. And a priori, this looks very complicated in three coordinates described by two equations. But then if you look at the coordinate ring, well, it's the quotient of the polynomial ring by these two defining equalities, because you can check indeed that this is the radical ideal. So this is indeed the ideal of x. And well, if you do that, then you can see that this ideal allows you to eliminate y and z, right? Replacing them by x squared and x to the 3. And so this is isomorphic to k of x. By the way, this shows that this is a radical ideal because this is a domain. And we know k of x from different contexts because it's just the functions on A1, of course. And then this abstract kind of manipulation of the coordinate rings immediately by the corollary tells us that then x is isomorphic to A1 via the map which sends x, y, z to x. And of course, you can then see the inverse of this isomorphism. You can just kind of stare at the functions here and then see the inverse is given by x is sent to x comma x squared comma x to the 3. So that's a parameterization of this rational normal curve. But we could also just see it by staring at the coordinate rings, which is very nice. And then you can use this this also to calculate some sets of automorphisms, which are isomorphisms from a variety to itself. And at least in some very small cases, these can be explicitly determined, namely the automorphisms of A1, the affine line, are just given by the functions f of the form f of x equals ax plus b for a non-zero number in k and b any number in k. So that's a nice exercise, and you can use these results saying that isomorphisms correspond to isomorphisms of the coordinate rings in opposite direction. Note that the automorphism group of A2 and all the higher ANs, these are actually extremely complicated. They're not describable in such an easy format. And there's actually papers of people studying these groups and trying to make sense of them. But at least for A1, it's actually just a short exercise to calculate this group. And then finally, a word of warning here, because I mean, in many areas of mathematics, it's true that you define morphisms to be, that you define isomorphisms to be morphisms which are bijective. This works in a lot of cases, like, for example, linear maps between vector spaces, and also continuous maps of topological spaces when you want to define homeomorphisms. But in algebraic geometry, this just doesn't work. And here's an example. So we have x, the vanishing locus of x squared minus y to the 3 inside A2. And this turns out to look something like this. If you want, this is kind of, I mean, when I draw the real picture, this is kind of looking like y is equal to the 3rd root of x squared. So this is one of these power functions with rational exponent, if you like. And you see somehow this is a sort of singular point in the sense that we define later. But so something might go wrong at this point, whatever we want to do. And then, well, at the moment, nothing goes wrong yet because we can define a morphism f from A1 into x, sending t to the 3 t squared. This certainly lands in here because, well, if you have t to the 3 squared, this is t to the 6 minus t squared to the 3. This is also t to the 6. So this is 0. So indeed, this is a well-defined morphism, again by the same criteria that we had before. And you can also check that it is bijective. And the set-theoretic inverse map is given by the map from x to A1. So if you have such a pair, and if y is non-zero, then you can get back this t just by computing x divided by y. because indeed then you have t to the 3 divided by t to the 2, so this just gives t back. And then the only point where this goes wrong is y equals 0, but if y equals 0, then this equation also forces x to be 0, and so this is only the point 0, 0. Well, this is the unique point in the image of t equals 0. And then you can kind of patch your map together. So away from the two origins, it's given by this map, and then you just by hand send this point to this point. So it has a set-theoretic inverse map, but the claim is F is not an isomorphism. It's a bijective morphism, which is not an isomorphism. Equivalently, this map F inverse is not a morphism. And certainly we can see here, well, at least the way we have written it down is not morphism. I mean, it is one away from y equals 0, but then we had to kind of by hand set it to be 0 at this point. And to show that F is not an isomorphism, we can now go to the commutative algebra side and just see what is F star. This would have to be an isomorphism, right? And well, what you do is you just plug in the definition. So again, this is a radical ideal. You can check that. And so a of x is given by this quotient here. It's sent to the coordinate ring of a1, which is k of t. And then this is just a map. You just look at the two components, and the coordinate function x is sent to t to the 3. And y is sent to t squared. And then, well, this is a well-defined K-algebra homomorphism. That's fine. But what you can check is, just for degree reasons, if you look at what are the monomials in each degree, you can check that t, the linear monomial here, is just not in the image of f star, because everything that you can get by either x and y has degree at least 2. And so this map is not surjective, and so it's not an isomorphism. So that's a word of warning that it's just not the case that any bijective morphism is an isomorphism.